All right, hey guys. Um, Welcome to today's lecture. It's going to be on a topic that I really enjoy, which is recursion. And it's something that is a very different way of thinking about solving problems. And so it's very challenging initially to grasp, but once you get enough practice with it, I think it's really cool. But first, I'm gonna go over some problems. This first one is dog breeder from yesterday, and it's a really good problem to basically go over not only higher order functions but also scope. And so let's get right to it. So this one is definitely a little confusing because of the fact that the function that gets returned from the original function, that function can take arguments that are pretty dynamic, and even in terms of where the order of the parameters, it can get switched up, and so it's definitely very tricky, but we can work through this together. So basically what this wants us to do is set these default name and age parameters that we pass in initially, and those are going to be the default, the fallbacks, and then the parameters that are passed into the function that gets returned. So those functions are, those parameters are the ones that can overwrite the defaults. And so let's just get started with implementing this. So again, we're setting defaults and we're only using them if they don't provide one of the parameters. So if they don't provide the name or age, then we're going to use the default ones that are provided initially. And if they provide only one of them, then we'll use the other one that they didn't provide. We'll use the default for that. So let's get started here. So we'll have a get dog breeder function, and this is going to take a name and an age. And basically what I can do here is essentially create a snapshot of these two variables of name and age that the return function will always have access to. So we can say let default name equals name, and we could say or we could just use const because we're not planning to change this. Default age equals age. And so these variables will always stay in the scope of the return function, even though the return function is called at a later time. It still has access to these two parameters. And so now when we do return function, and this function could have a name and age as well. So we can just give it, trying to think if this is going to have any collisions. It shouldn't, because it'll create its own local version of that. So what's really cool about JavaScript is that here, when we set these, this returning function will always have access to these, even though it's called at a later point where it would seem like it doesn't have access to these variables, because we can't explicitly see the internals of this function. This return function will always have access to these variables. And so it's almost like JavaScript is providing a snapshot of these variables, and this function will always have access to this because it's within the scope of within like this return function's global scope, if that makes sense. Even though that's the local scope of this function, it still has access to those. So here we can just say in this function, we'll have to do a little bit of type checking to see, because there's so many different variations of parameters that can get passed in. We can just, I'm just going to go for the simplest case right now. So if, you know, well, I guess we'll start off with the name. So if I shouldn't even call this name because it could technically be age. So I'll just call them input because technically the first argument doesn't even have to be a name. So it's like kind of confusing if I call it name. So I could say if input 1, if it exists, because it might not even exist, and type of input 1 equals string, I'm just going to say that if it's a string, then it's going to be a name. Then I could say, let me just create a variable of name, and I'm just going to set it to default name for now. But if we are given an input, then we want to overwrite that with input 1. Because right now we're just setting the name to be default. But if we're provided a name that should overwrite it, then I'm going to overwrite it here. And same with input. Let's see. Okay, so this is a little tricky just because there's different. It can have. This can also be a age actually. So let me just take that out and say if type of input 1 equals string. So if it's a string type, then, and in actual JavaScript, you'd probably never want to make a function that like can take parameters in all sorts of crazy orders. You'd probably want to restrict it so that it's a little, you don't have to write code like this, you know, it's just to do all these types of crazy checks. But in this case, we kind of have to. So here, if it's a string, then I'm going to overwrite my name with input 1. Else, if it's not a string, I'll just assume it's a number. And we'll just call it, we'll just say age equals input 1. And then same with input 2. If input 2, I'll just do the same thing. And then finally, I'll just return an object with name and age. So Arthur asks name and age equals input 1. I'm not sure what you mean by that, but there's probably a cleaner way. Oh, on 10 and 12. Oh, yeah. Good catch. Thank you. I'll just change all these to input 2. Yeah, so because of this weird function signature, and yeah, again, I would like to stress that you probably don't want to write a function that like can take in parameters in different orders and have them be different types and all this stuff so that you don't have to do all of this, all these checks. It kind of makes the code a little messier than it has to be. But I think the main important idea to get from this is that this function that's returned, it'll have access to these variables that you set. And this is called closure, the actual term for basically a function keeping the scope, keeping all the variables in its scope when it was declared. Whenever it gets called, it still has those variables in, that it's able to access. So that I think is the important takeaway from this. So yeah, this is just, I mean, the fact that these can take weird arguments, I wouldn't stress too much about that because you probably won't see that in the wild. Is if somebody made a function like this, they would be confusing a lot of people. So Jackie asks, do we have to do the declarations of line 4 and 5? Or can we have the outer func accept defaults. Do you mean this? But do you mean this as the outer function? Yeah, I guess we don't have to call it. Yeah, so I guess we can just say, let's see. But then, I mean, if we don't have to do this, we technically don't have to do this, but then that would mean that we would have to change this name. We would have to say like let result name or something equals name. Like we don't have to name it that, but I just named it that just so that it's more clear. Like this is a default name, this is default age, and then this is what we're actually going to be returning. Technically, we don't have to do this, and we can just use name and age as they're passed in. We don't have to change the name, but I just did that because otherwise I would have to think of creative names. So I would have to say, you know, result name or something equals name as the default, and then reassign it if it needs to be overwritten. But I just wanted to make the naming clear. But good question. So yeah, that's pretty much it for this problem. Are there any other questions on this? Again, whenever a function is declared, it'll have access to whatever is in that function's scope. Whatever variables it can have access to, it'll have access to them even though they're called at a later point where it doesn't appear like there's access to those variables, it'll still maintain access to those. And if you guys want to read more about that, you can look up closure in JavaScript, and it'll basically give a lot of examples of this. Okay, so we'll go on to the next problem, which is cache savings. And this is something that's really useful in my opinion, just because a lot of emphasis is placed on performance in web applications. And so if you've done a computation already, chances are someone's going to want you to do it again. And if you've already ran a function and obtained the results of that function, there's really no point in running that again because you have that value if the input is the same, obviously. So we can just save that value somewhere and then access it really quickly and not have to run that function again. It's almost like if you had to file your taxes and you, at the end of it all, you get how much you are owed, and then every time you want to access how much you're owed, you'd probably just write it. You'd probably write the result on a piece of paper and then just look at that piece of paper. You wouldn't do the calculations all over again. So this is pretty much just a performance enhancing tool. And so basically we just want to say that when we initially call a function with an argument, we want to calculate it because it hasn't been calculated before, but the next time we just save that value somewhere and then we access it without having to do all these calculations. So yeah, it is going to take a function that takes an argument. So let's just create that. So this is a function. It's called cache savings. And it takes a function. It takes a callback function as a parameter. So it takes a function. I'll call it func so it's clear. And essentially what it's going to do is it's going to return another function that's going to take the actual argument. And this, in this case, happens to be a number. And so here, in this function, we're going to actually call at some point, we're going to call this function that we're passed in and then give it the argument that's passed into this function. So how we can use a cache is, it's the same thing as before. where we essentially take advantage of JavaScript's sort of snapshot scope functionality, where we have access to these variables, where this function will have access to these variables. And so we can just declare a cache. And there could be multiple data structures you could use, but I would say that an object is the best just because the lookups are instant. So if we kept it in an array, we could technically keep it in an array, but we might have to iterate through the array to find whatever value we're looking for. Whereas here we could say, oh, have the argument be the key. So, when we call the function with 20, 20 will be the key, and then the value will be whatever the return value of the function is, so that we can easily check in this object if that argument exists as a key. And if it does, that means we've already run the function before with that argument. So initially I'm just going to declare this cache here. And then here I'm going to say if there's nothing in the cache for this argument. So when we first run this function with cache savings, when we do cache adds 10, and then we pass in 20, the cache can be empty. We've never ran the function, so we don't have any value that's saved. So it's going to go into this case that it doesn't exist in the cache. So if it doesn't exist in the cache, then we're going to add it to the cache. And then, does anybody have any idea what this value should be? What value we're saving? So in this example, we're passing in 20. So it would be like 20. And then what would the value of 20 be? Exactly. So callback func arg. So we're storing the value of this function in this object. Beautiful. And then anybody have any guesses what we're going to return from this function? So when we call callback adds 10, how are we going to get the value that we're looking for? How are we going to get 30 from that? Yep. Great answer. It's just cache arg. And that's pretty much it. And what's cool about this is, when we call it with 20, initially there's nothing here. So we'll do 20 and then we'll save the 30 as the value. And then next time we call this function with 20, it's not even going to call the function. It's just going to skip this entirely because 20 does exist, and it's just going to return the value of 20 without even running the function that we passed in, which is cool. We're saving a lot of calculation. We're saving the engine extra work. So yeah, that should be it for this. And this is a very useful concept of not having to do extra work when you don't want to. But I think it points out a very fundamental concept, which is that in engineering, as in almost anything, everything is a trade-off. So although we're saving time by not having to calculate this, if we've already done it in the past, we're sacrificing memory. We're forcing the program to store more objects in memory. So as this object gets bigger and bigger, as it grows and grows, we're basically using more and more memory, but we're gaining performance in terms of how much time it takes. So usually memory is cheaper than time. Like, we would rather just take a lot of memory and then have everything run really fast. That would be optimal. So usually we're fine with that, but it's always a give and take. When you save on one thing, you're sacrificing something else. So are there any questions on cache savings? If not, then, line 6. So line 6 is basically saying, does my argument exist as a key in my cache? Which is another way of saying, have I ran this function with this particular argument before? If I have, then this cache arg should be truthy. And so doing a exclamation point in front of it should make it turn false, and then it won't even go into this else. I mean, it won't even go into this function if we've already called it. So, for example, if 20, what's the answer to 20? If 20, 30, if the object looked like this, then cache 20 would be true. It would evaluate to truthy. And so when we do a not in front of it, then it would become false. And then we would just return the cache argument because it does exist. If it didn't exist, so if the object was empty, then cache arg would be undefined. And undefined, putting an exclamation point in front of undefined, it'll be a double negative, and so it would turn it true. And then so it would run this, meaning that the cache is empty or the cache doesn't contain this key. And so I need to run the function to get the actual result value for the function being called with that argument because it doesn't exist in my cache. So that's sort of what line 6 means. And it's a little confusing because I'm using the not in front of it, which just means like I'm basically saying, does the fact that the arg not existing in the cache, is that true? Like, is the fact that the cache arg is undefined, is that true? Is what I'm basically asking. But I could have done something like if cache arg equals undefined. I think I could have done this too. And Arthur asks, does the cache have to be an object? It doesn't have to be an object, but you could do something like have it be an array. Actually, it'd be tough for it to be an array because then you would need the key and the value. So it would need to be like something like this, where 20 is 30, and what are the other ones? 0 is 10. So it would just, and then for us to find it, it would just take more work because we would need to go through and this array and figure out find the element where the element at the 0th index equals the arg, and it would just be like a lot of extra work. So Arthur asks, you're asking great questions, by the way, just keep these coming. So we only need to store one value. You're correct. For the, in the real world, we would use an object just because it's just instant lookups. So we would use an object. But for your first question of we only need to store one value, we only need to store one value for one argument. So when the argument is 20, then we would store 20 is 30. But then the next time it runs, when we run it with 0, it needs to be 0 and 10. So we need to store multiple things. Like it's not just one argument, because every time if we do 30, then we would need to store this, and then 40, and then it would store this 50. So it needs to be an object, or it needs to be something that's more, you need an arg and a result stored, and then there could be multiple args. But then if you just had two variables, then you could only store one at a time, like one argument at a time. If you kept it an object, it could store as many arguments as possible. And in the real world, you want an object because it would save you from having to iterate. And you could just say, does argument exist in the object? And that lookup is instantaneous. Whereas if I needed to search an array for a value, it would take potentially we would need to potentially loop through each item in the array. And that would take time. that's not an insignificant amount of time if the array was really, really large. So if the array is small, then it wouldn't really make a difference. But if it was really large, then we would need to go through each item and try to find something, and that would be suboptimal. Yeah, this is a tricky one. It's definitely hard to think of, and it's not a concept that we're used to. And honestly, it performance is just something that you'd want to address if the time comes. There's no sometimes it would be not the best use of time to try and optimize for performance all the time. It's really just get this thing done, get it working, and then if it's too slow, then we'll figure out how to make it faster. But yeah, this is something that I would say is an important concept because it's really used everywhere that we look. Every single time we go to a website, those files are unless you disable caching, a lot of stuff is cached, like images, they're cached on your browser. So every time you visit something, you're not reloading everything and having it do all that work. You're just basically storing these files and just displaying what's saved locally in memory. So a lot of this, it's just ubiquitous in development to have these caches because otherwise things would take a lot longer. So Raymond asks, is a good use case for this would be saving search values? Yeah, we could cache search values. You could cache almost anything you want if it's too slow. If recalculating something each time is too slow, then you could definitely cache things. So on Google, if you had a bunch of results for a search, you could cache the results so that next time they type it, you're not actually going through and aggregating all those pages. You just have that list and you just show it to the user. One downside of caching, though, is that when you have new results, then you have to break the cache, and that's challenging. So there's always a give and take, as I mentioned before. If, for example, if for Google search, when you typed coronavirus and you cached the results, but then 2 days later, there's all these different results now, like the algorithm changed a little bit, the order changed, but you still have the old values because you haven't updated your cache. And so the need to update caches makes things a lot more complicated. So yeah, there's always pros and cons to it. But to your point, Raymond, it's a good use case. Are there any other questions? Again, an important concept here is closure. When we declare a variable, and then this function that's returned will always have access to this variable, even though we're using it outside. Technically, we're using it outside of this scope, this cache saving scope. When we call it, it's not in that scope, but it still maintains a reference to this variable. It still knows what cache is. And again, the technical term for this is closure, and you could look it up and read some Medium articles about it. It's really something that's commonly sort of expected for JavaScript developers to have a grasp of, because it's really useful for things like this. All right, so if there's no other questions, I'm going to go on to the lecture now about recursion. And it's definitely a challenging concept, but it's also lots of fun, and I think it's really cool. So, all right, let me figure out where this is. Okay. I have a PDF version of it just because my Keynote is acting up right now. So recursion. We're going to define recursion, and then we're going to get a little bit into the weeds of how JavaScript works when it's working its way through a program, how exactly it knows what functions to call and basically where it is in the program. The call stack is going to tell JavaScript where it is in the program, what function is running, what functions to run next, and things like that. And then we're going to go over a couple examples and then a couple tips for approaching recursion problems. So here we go. So I alluded to this a little bit in earlier lectures about when we had those nested arrays, for example, and we were trying to flatten them. And we were pretty much doing the same thing that the function was doing, except we were doing it one level nested deeper. And so we could have just used recursion for that, which is basically when a function calls itself. And it is a little bit confusing initially to think about because this idea is foreign of using the function to solve, calling the function again, as opposed to just, write normal code. We're going to just skip a lot of work and just call the function again. It may be tempting to think that this is different than a function calling another function, but it's really not. It's just this, we could think of it as if it was a function that calls a whole new function, and it'll basically function the same way as that, but it's just a little more confusing because it's calling itself. But we can just like how back then when we learned about higher order functions and we just said, let's just treat functions the same way as strings and numbers, and in terms of the fact that we can return functions from functions and also accept functions as parameters. We can also think of that with recursion as well. Even though it's a function that calls itself, we can just think of it as a function that calls a different function, if that makes it easier to reason about. And so we'll get into more of how this might be useful later on as we go through this lecture, but basically it's an alternative to using a loop. So anything that you can do, any problem you can solve with a loop, you can also solve with recursion. And so why would we need recursion? Sometimes it helps to think about a problem in different ways. So in an iterative solution, we think about just solving the problem in steps using, each iteration is a step and we're getting closer and closer to the end. But recursion, you kind of think about it in terms of a problem and then breaking it down into like smaller and smaller problems. So for example, let me give you a quick example. So if we had a list, right, an array 1, 2, 3, and we wanted to figure out how to find the sum of all the elements in this array, well, we would just say, use a loop and then, get, for element in array. I'm just doing pseudocode because I don't want to code it all out. We'd have a sum, set it to 0, and then do sum plus equals L, and then at the end, we just return sum. So that's the iterative approach. But let's say we want to break this problem down into smaller and smaller problems, smaller and smaller subproblems. So we could say sum equals array at 0 plus array.slice1. And so that really means like the sum is like 1 plus 2 plus let's say there's a function sum that just takes a list. Basically, we could say, array, the sum of this is the first element of the array plus everything after the first, calling sum on everything after the first. So essentially we're saying sum of this is 1 plus sum of 2, 3, like breaking it down to smaller problems. And then after that, we can even break it down further. So we could say this is basically, 1 plus 2 plus sum of 3. Like basically taking off the first element and then breaking it down into a smaller sub problem. And then once this hits, then it's 1 plus 2 plus 3 plus, and then like sum of empty array, which just would be 0. We could just set it to be 0 if it's an empty array. So this is kind of what I mean by breaking a large problem into smaller and smaller problems, as opposed to just thinking, oh, I'm going to do this series of steps, where it's a little different. When we think of the iterative solution, we're thinking just, oh, a sequence of steps where we're just going through each element. We're not really thinking about breaking the problem into smaller and smaller problems and like solving the simplest case first. And so this, in recursion, it really helps to think about solving the simplest case first. So, if I have an array of 1, 2, 3, let me figure out how to get the sum of an array that's just an empty array first. And then let me try to figure out how to get the sum of 1 list. And then 2, and then once I have that foundation, theoretically I should be able to find an array of any length, the sum of that. So that might have been confusing, but we'll get to, we'll like review this one more time. But I wanted to give you guys a example of what I mean by breaking a problem into smaller problems. So it's really, the point of this is to learn that, and to sometimes for really complicated problems, the recursive solution is a lot cleaner. It looks a lot cleaner than an iterative one because you don't have to really write too much code. You just call the function again. However, it can be detrimental because it can use a lot of memory, and I'll show you why that makes sense. Because basically our call stack becomes a lot larger than it really has to be with recursion, but it still can provide the benefit of keeping your code at least looking more clear. And it's just a common topic that people ask about in interviews and things like that too, just because it just tests, like, I guess, how you can, break a problem down into smaller problems and things like that. So I wouldn't say it's that common to find in the wild, but it's definitely a common thing to be asked about in interviews. So the call stack, we need to learn about this first before we learn about recursion. So JavaScript is single-threaded, which means it can only run one function at a time. And the way that it figures out which function to run is the call stack. And so the call stack is, we could think of it as just a stack. We could think of it as just an array, and we just push into that array and then we pop from that array. And basically, we can think of it like a stack of papers, a stack of pancakes. So basically, when we call a function, it gets added to the top of the call stack. So in this case, we add first to the call stack, and then we run that function. So we add first, it's being invoked. And so once we invoke it, we just console log I am first. That's what we see at output. And then we pop it from the stack because we're done running that function. And then now we have second that we place onto the stack. And then that function will run its inner contents. And then it'll log I am second. And then we're happy. We pop that off the stack. And now the stack's empty again. So now let's get a little more complicated. So, and this is kind of like recursion, except it actually is exactly like recursion, even though we're calling a different function in here. And in recursion, we would be calling the same function. It's really the same thing. So here, how this will look is we'll put first onto the call stack right here, first. and then we log I am first, and then we put second onto the call stack before we can pop first off, because we can only pop the function off of the call stack if it's done running. So if it's done running, then we remove it from the call stack. JavaScript doesn't have to think about it anymore, and we go on to the next one. But because this second function is called before the first is done running, then we have two functions on the call stack now. So first is still technically, it's not done. It's still, JavaScript can't just disregard it anymore because it's still running in the background. But now second's running. And then so JavaScript has to sort of multitask in terms of it puts, first in the back of its mind. It's still keeping that in its mind, but then it has to focus its attention on second now. And when we come to recursion, we'll see that this is the exact same idea, is that even though we're calling the same function, it still places that function call onto the call stack. And then that initial call is still also on the call stack too. But it's a little easier to reason about calling an entirely different function because we're more used to seeing this. But it really will work exactly the same way with a function calling itself. And we might have a question. So are they being executed simultaneously in this scenario, or is it like a queue? So that's a great question. It's not simultaneous. It is like a queue, but it's actually a stack. So a queue is a little different from a stack in that in a queue, you execute things in the order that they came in. So it's like a line. Like when you stand in line, the first guy in line gets to order his food, and then the last guy has to wait. But this is a stack where the last guy gets his stuff first. So it's kind of reversed. So it's not a queue, it's a stack. But it's like a stack of pancakes. Like you stack the first pancake on, but the first one doesn't get eaten first. The last pancake you stack on gets eaten first. So it's sort of like that. But in terms of it being executed simultaneously, it's not. That's what it meant by JavaScript is single-threaded up here. I don't want to go all the way up, but JavaScript is single-threaded, meaning it can only do one thing at a time. But it can, as you alluded to, it's sort of like a queue where it like keeps things in the background, and it's not working on them at that time, but it knows to get to them eventually, and it'll be focusing on only second at this point. But first is still, as you mentioned, sort of in queued, but that's a little confusing because it's really a stack and whatever. Yeah, it's the pancake analogy. Basically, first we stack the first pancake on, right? But that first pancake told us to add another pancake. And then so we added that second pancake. And then now we're working on the second one. Even though it came in last, it's still being worked on first. Exactly. Elizabeth said we're storing it on the call stack so we can access it again eventually. Exactly. We're not done with first. We still need to do stuff with first. We're not done with it, but in the middle of it, it happened to call another guy, its friend, and said, first you got to deal with my friend before you're done dealing with me. And so JavaScript was like, okay, like now I can only do one thing at a time, so let me like work on your friend, and then I'll finish you up after. So George asks, if line 4 didn't exist, would first be done at like 3? So that's a great question. It won't, because basically this function has to be done running before first is completely done. So it would still happen the same way. You put first on, and then you log this, you log I am first, and then you call second, and then you put second on, and then once second's done, then first is also done. So it would act in the same way. Like even if line 4 didn't exist, it would still act the same way because first can't be finished until second's finished, if that makes sense. So it would still, the call stack would still look like this. and again, I want to reiterate, when we do recursion, so this function would be recursive if we called first, right? Then it's technically a recursive function. But it would still happen the same way. We would have first, and then we would just put first again. Like instead of second, it would be first. But it's just the same thing, really. And so yeah, first is paused while second ran, because second was like, hey, can you eat my friend first? And so the friend pancake goes on the top, and then you eat that friend pancake, and then now you can finally eat the first pancake. And first is finished, and then we popped second off when we were done with it, because when second's done running, we pop it off. And then now first is done because we've finished second. First can't finish until second finishes. It's a prerequisite. So we're done with first, and then we go on, and now the call stack's empty, and we know we finished this mini program. We're done running the program. So are there any questions on the call stack? And when we go through recursion, it'll help to have this call stack in mind, just because it will help make sense of things, especially when we start returning things from problems. But yeah, it's definitely a tricky concept, but knowing the call stack and knowing that it exists and knowing that a function calling a different function completely is really no different than a function calling itself, I think it'll help ease this learning process. So yeah, that's pretty much it about the call stack, but we'll still refer to it as we take on more challenging problems. So we're going to go over this example of write a function that counts down to 1 given whatever input we give it. So initially we might think we'll use a for loop, and I would think this too. It's, the iterative solution, and we just, go through and log. Nothing special here. But how about, if we simplified it, we just took out the loop and we just try to break it down and set into smaller and smaller pieces, and try to use the function itself to solve this. And so essentially we could call countdown multiple times like this. If we simplified it out so that it did the bare minimum, and we just called that same function, obviously this is manual, so like it would take a lot more work because we're literally having to write each iteration down. But this is a really good clue about, hey, we're using the same function to solve it, so we're going a step towards using recursion. But in this case, it seems a little manual. So we want to allow the argument to change between calls. So how would we do that? Well, why not just console log the number, right? So, when we do countdown 5, it'll do countdown 5, and then it'll just call countdown 4. This seems like a promising approach because we're using the same function to call itself, and we're solving this problem because it'll log 5, and then we'll call countdown 4, and countdown 4 will log 4, and then it'll keep going and going. But if you guys don't see, does anyone see a problem with this potentially? So we call countdown 5, and then it calls countdown 4, and then we log 4, and then it calls countdown 3, and then we log 3, and then it calls countdown 2. Yep, it goes on infinitely. Exactly. You guys are ahead of the game here. But let's just take a look at the call stack just for practice. Just move this, make it a little smaller. Still want to see this though. So countdown 1 gets placed on the call. Countdown 5 gets placed on the call stack. And then afterwards we call countdown 4, but we can't pop countdown 5 off because we're not done, because countdown 5 can only be popped off when countdown 4 is done. But countdown 4 isn't done yet. We just called it. So we have countdown 4 on the call stack. And then countdown 4 calls countdown 3. And then so we have countdown 3 in the call stack. And nothing can get popped off because there's no stopping this. Technically, countdown 4, like, so when we called countdown 5, we called countdown 4, but we can't pop countdown 5 off until countdown 4 is done. But we can't pop countdown 4 until countdown 3 is done, and we can't pop countdown 3 until countdown 2 is done. But it's never done. No function ever finishes because it keeps calling a different function over and over and over, and then it goes, and then it goes, and then it goes to the negatives now, and we still haven't popped anything off. And each one of these calls takes memory in the engine. Elizabeth, yeah, exactly. We can break from it. And so we're going to get to that. But this is just a common thing people run into when they use recursion, is that they forget to create a base case or a case where we just return some value instead of calling the function again. In recursion, we always need at least two different paths. We need one path where it calls the function, because that's the definition of recursion, is that we need to use the function we need to call the function to solve the problem. But we need another path where we just return a number, or we just do something. We don't need to necessarily return, but we can just do something that doesn't involve calling the function, because we can't just have one path that just calls the function, because then it's just going to keep calling things, and then it's never going to be able to stop calling itself. And each one of these lines takes memory in JavaScript, and so JavaScript doesn't have infinite memory. There's a lot of memory, but it's not limitless, and so it's eventually going to hit a ceiling, and we're going to explode our program because it's going to maximum call stack size exceeded, and it'll just break. So we need a stop condition, and essentially we refer to this as the base case or the non-recursive case, where we just do something. We don't need to necessarily return anything, but we can just run a bit of code that doesn't call the function. So here it is. This is our stop condition right here. So if the num is less than 1, just console log done, and don't call the function again. Else, call the function. So now this fits into our case where, we're not endlessly calling the function without any constraint. There is a constraint now. If the num eventually, and this will eventually happen because we're decrementing by 1 each time, when the num is less than 1, we're just going to console log done. And then at that point, that function is done running. So when that function is done running, it can start popping things off of the stack. And we want that because we eventually want to clear the call stack and finish running our function. So when we have, countdown 3, it's going to place countdown 3 onto the call stack. And then countdown 3 is going to call countdown 2, and then it's going to place countdown 2 into the call stack. It's like a U-turn where we just, exactly, that's a great way to think about it, is it's like a U-turn where, we're driving along the street, and then we just take a U-turn and we drive all the way back where we came from. Or it's kind of like diving underwater. Like when we're calling recursive functions, we're diving to the ground. And then once we hit this base case, we start swimming back up. And as we go back up, we start popping things from the call stack. So here, we call countdown 3, that places countdown 3 on the call stack. And then we log 3 because before we called countdown 2, we logged the 3. And then we call countdown 2. We still can't pop countdown 3 off because countdown 3 can only be popped when we're done running countdown 2. And we're not done running countdown 2 yet. So we put countdown 2 on the call stack, and that logs 2. and then we call countdown 1. That puts countdown 1 on the call stack, and then we log 1. Now we call countdown 0, and this is the special case where we just log done. So we call countdown 0, and then countdown 0 is done now. It can be popped off the stack because there's no more code to run here, and it didn't call a function that hasn't completed yet. So countdown 0 is done. Like, we're done running it, and it can go off the call stack. And what's cool is that because countdown 0 is done, countdown 1 is also done now, because countdown 1 was just waiting on countdown 0 to complete to itself be able to get popped off the call stack. So when countdown 0 finishes here, countdown 0 finishes on line 5. Countdown 1, which was waiting for countdown 0 to finish on line 10, because countdown 0 was called on line 10, it's done now because countdown 0 is done running, and that's the only thing it was waiting on. So now countdown 1 can get popped off. So countdown 0 got popped off. It logged done because that's what it does. And then now countdown, after countdown 1 gets popped off, countdown 2 can also get popped off. And then also it just bubbles back up to countdown 3. And then we're done. Are there any questions about this particular problem? It's definitely a little tricky, but the two main concepts are base case, where we don't want to call the function again. We definitely don't want to do that. We don't necessarily need to return anything, but we just need to do something where it doesn't involve calling the function again. And then in our recursive case, we actually need to call the function because otherwise it wouldn't be recursion. And we want to get at each step, at each function call, at each recursive call, we want to get closer to the base case. And how we're doing that is we're decrementing the argument by 1 each time so that we're getting closer to this case being true. Because if this case never reaches, then we're also it's just gonna be infinite. So Katie asks, if num less than 1 is the base case, that stops the function. Yeah, exactly. That stops one of the functions. So that stops countdown 0. So when we do countdown 1, right, that console logs 1, and that calls countdown 0. And so it puts countdown 0 on the call stack, and then this base case stops countdown 0. It doesn't stop like everything, but it stops countdown 0. Like, it allows the countdown 0 function to complete. And once that completes, it can get popped off the call stack. But the beauty of this is that when countdown 0 is done, then that enables countdown 1 to also be done, because countdown 1 was waiting on countdown 0 to complete. It couldn't get popped off until countdown 0 gets popped off. But since countdown 0 was able to complete, now we can complete countdown 1. And then that triggers just a cascade of all of the ones above it that called it to be able to complete. Does that make sense to people? So yeah, like, I mean, essentially we could think of it like a movie. I was trying to research some ways to explain recursion, and one way that I really liked was, think about if you're sitting in a movie theater and you want to figure out what row you're sitting in. You could go out of your row and then just walk down. That would be the iterative solution, is like you go out of your row and then you start walking down and then count each row like a for loop. Or what you could do is you could tap the guy in front of you and say, hey, like, can you tell me what the guy in front of you, his row is? And then that guy would tap the other guy in front of him and say, oh, can you tell me like what row you're sitting in? And then that guy would tell the other guy in front of him, and then the guy in the first row would be like, I'm sitting in row 1. And then so he would so that would be the base case. The guy in row one would say, I'm sitting in row one. There's no one in front of me, so I'm row one. And then he would tell the guy that tapped him, hey, look, I'm row one. And then the guy that tapped the guy in row one would be like, okay, so I must be row two because he just told me he's row one, so I'm going to add one to that. I'm row two. And then the row two guy tells the row three guy, he goes like, I'm row two. So then the row three guy's like, yeah, like that must mean I'm row three because one plus the guy in front of me. And then all the way back up until I finally get my answer. So that's what it means by like, Elizabeth said it's kind of like a U-turn. And it makes sense. Like you're going first, it's got to go down all the way from the top. It's got to go all the way to the first row without getting any answers back. And then the first row guys, the base case, tells all the guys that called it the answer. And then it just bubbles back up the rows of the movie theater. So that's kind of like two different approaches of recursion versus iterative. But if this doesn't make too much sense, we'll see an example of like returning, because this example doesn't return anything. And so I guess the movie theater example doesn't make too much sense because the movie theater example is more for when values are returned. So, you're sitting in your row, you ask the guy in front of you, that guy asks the guy in front of him, that guy asks the guy in front of him. And that's sort of like, diving underwater and going to the ground. And then once you hit the ground, the first guy knows his answer, so he gives it to the second guy, and the second guy gives it to the third guy, and then we bubble all those answers back up to the surface. But we'll get more practice with this if that was confusing. But yeah, that is pretty much it for countdown. Is there any more questions about this particular example, the countdown example? If not, we'll do the two takeaways, base case and recursive case. And again, the recursive case, you have to change the input in some way to get it closer and closer to the base case. So we can't do like num plus one here because that would make it further from the base case. We need to get closer to the base case. So now returning from the recursive call. So this should help make the movie theater example make sense. So recursion becomes a little more complicated when the function must return a value. So again, we still need to define a base case. So this is a good pattern to keep in mind, is that a base case is often the simplest input. So, or base cases are often occur when there's a simple input. Basically, the base case a lot of the time for numbers is like 0 or 1. I'm not saying this is going to happen 100% of the time, but a large majority of the times, your base case is when your number is 0 or 1. For an array, your base case is usually when the array is empty. And for a string, it's usually just an empty string. That's usually like your base case, like your most simplest case. Start off really simple. So for factorial, we'll go through an example of returning from recursive functions. So factorial, we need to, let's just review what problem we're trying to solve. Basically, we're just multiplying that number by every single number that came before it, every single integer that came before it, all the way up to 1. And factorial of 0 and factorial of 1 is always just 1. Those are like your base cases. Like, we just had to accept that as a rule of factorials, that factorial 1 and factorial 0 are always 1. So it would make sense that this is like your base case. And so we could say, oh, look, if the num is 0 or num is 1, then just return 1. And then this is simple enough, our base case. Now we need to figure out our recursive case. And the cool thing about factorials is that essentially a factorial is basically that number times the factorial of n minus, or that number minus 1. And yeah, this is just a pattern that just occurs in factorials, because if you look at 2 factorial, it's basically that number times 1 factorial of 1. And factorial of 1 is just 1, so it's just 2 times 1. For factorial of 3, that's 3, that number, times factorial of 2, which is 2 in this case. We solved that already. It's 2, so it's just 3 times 2. Factorial of 4 is 4 times factorial of 3, and we've already solved that already. It's 6, so it's 4 times 6, which is 24. And so that's like a pattern that we can see. And so this looks like it's the perfect use case for recursion, because we can just call that same function and pass it a little bit of a smaller parameter each time. So how do we do this? Well, we need to get closer to 0 or 1. We need to somehow figure out how to get closer to this base case. So if we did factorial 2, right, then it doesn't fit into here. So in this recursive case, we still need to call it. So how do we do this? Well, we could, try and figure out what would happen if we called that same function with num minus 1. So what would happen in this case? So if we did result equals factorial 2, it would basically be undefined, because we're just returning, when we get here and we're trying to save the value of factorial of 1, this would call factorial of 1, which returns 1. So this console logs 1 to the terminal, but the actual return value, the result, is undefined, because we're not returning anything here. We're just console logging something. And so whenever we have a function that logs and doesn't return, then it just automatically just undefined. So result of factorial 2, console log of result, would be undefined, just because we're not returning anything here. We would need to return something here in order for this not to be undefined. Now, you guys it might be a little confusing, because factorial of 0 and 1 does return something, and we're calling that, right? But we're calling it, but we're not returning it. So just calling a function also would just return undefined, because we are calling factorial 1. When we call factorial 2 here, we don't go into this case, because the num is 2, so it doesn't fit here. So we go to line 9, and then we console log factorial of 1, which is, it returns 1. So this function call becomes interchangeable with the number 1. And so we console log 1, but then that's it. And then it just, we're trying to save that value, but we have nothing to save because we never returned. Does that make sense to people? It's a little weird, but in order for us to have a value for this result variable, we would need to return something on line 9. We can't just console log. It does call the function recursively, but there's no value to be saved. So maybe we'll try, console. We're getting closer to the answer now, but this time we're console logging num times factorial of 1. And so that means that factorial 2 actually logs the right answer, but it doesn't return it. And logging and returning are two totally different things. So let's walk through what happens here. We call factorial of 2, right? And that goes to line 8 because it doesn't fit with line 3. So we console log 2 times factorial of 1. And factorial of 1 is 1. It returns 1. So we console log 2 times 1, which is 2. But the result is still undefined because we're not returning in line 8. So we're getting closer though, because 2 is the right answer. We just need to return. So then now if we just return, then we get the right answer. And this is the solution for factorial for 3 and 4 and 5 and 6 and 7. It all works the same way. And we'll see how this will make more sense when we look at the call stack. But we essentially need to return here in order for this to work. And so this is actually the solution here. So now let's get to the call stack. So what happens here when we call factorial 5? So when we call factorial 5, we place factorial 5 on the call stack. And then we do line 7, right? We do 5, result equals 5 times factorial 4. But we can't pop factorial 5 off the call stack because it's not done running, because factorial 4 is not done running. So we got to put factorial 4 on the call stack now, because that's what's called. And we don't know what that answer is yet, because we haven't, because factorial 4 is, we haven't executed that function. So let's just put 5 on the call stack for now. And then the value is going to be 5 times factorial 4. And factorial 4 hasn't completed yet, but we need to put that on the call stack because we do call it, right? So we put factorial 4 on the call stack. In factorial 4, same as factorial 5, it runs line 7. And it does, result is 4 times factorial 3. But we can't pop factorial 4 off because it hinges on factorial 3 completing, and factorial 3 hasn't completed yet. So let's call factorial 3 now, put that on the call stack, and then factorial 3 goes to line 7, it executes 3 times factorial 2. Now we can't pop factorial 3 because factorial 2 needs to finish running, and factorial 2 hasn't finished running. We called it now so we can place it on the call stack, but yeah, it still hasn't finished running. But here's the beauty about factorial 2. It calls factorial 1, and factorial 1 returns immediately. It doesn't call another function, so we don't need to place another function on the call stack. Basically, when factorial 1 gets called, this function call is basically just interchangeable with the value 1 because we're returning 1. So Jackie asks, so is the num or num equals 1 to save time? You mean like, technically, I don't even think we need or 1. But I think this is a rule of factorial. This is a great point. I don't think it matters. You could leave it out. I mean, it'd still work. But I believe like the technical definition of factorials is that a factorial of 0 and a factorial of 1, they're both equal to 1. That's just almost like a part of the math. Exactly. Yeah. It's just the definition of factorial. Just like how anything, to the power of 0 equals 1. And that's just like a rule. That this is much the same thing. In this case, you're right though, we wouldn't need it. But here, the beauty of factorial 1 is that it just returns 1. And so just like any other function call, when we call a function that returns something, we just switch that function call for that value. It's just that they're interchangeable. So this value becomes 2 times 1. And what's awesome is that now factorial 2 is done because factorial 2 is equal to 2 times 1. And so now factorial 2 can get popped off the call stack because we're done running that, right? Because factorial 2 was just waiting on factorial 1 to complete. But factorial 1 completes immediately. It doesn't call a different function. So factorial 2 is done, right? And its value is 2 times 1. So now factorial 3 can also be done because factorial 2 becomes interchangeable with this value, which is just 2. So now factorial 3 can be done because 3 equals 3 times 2, which is 6. And it bubbles all the way back up. So factorial 3 gets popped off. So yeah, let's just go through this step by step. So factorial 1 is done, gets popped off. Factorial 2, now it has that value of 1, and so it can get popped off. Factorial 2 is just going to be equal to 2, and so it's popped off. And then now we replace factorial 2 with just the number 2 because that's what it equals. And then we pop 3 off because now 3 is just equal to 6. This 3 times 2 is equal to 6. And then we pop 3 off the stack. It's almost like the movie theater example. I'm sitting in row 5 and I ask row 4, hey, what row are you in? And row 4 asks row 3, hey, what row are you in? And like none of those, we haven't gotten answers yet. The answer is almost like the return value. Once we get the answer, we can, we don't need to care about the person in front of us anymore because we've already gotten our answer. So the guy in the 5th row of the movie theater asked the guy in the 4th row, what row am I in? The guy in the 4th row asked the guy in the 3rd row, what row am I in? The guy in the 3rd row asked the 2nd row, what row am I in? The guy in the 2nd row asked the first guy in the 1st row, what row am I in? And then the first guy's like, I don't need to ask anyone. There's no one in front of me. So I'm row 1. And he tells, now it's returning. So the row 1 guy says, I'm row 1. And then the row 2 guy's like, okay, so he's row 1. So I'm row 2. And then he gives it back to the row 3 guy. He like passes the answer back, all the way back, all the rows. And then the row 3 guy's like, okay, so I'm row 3, tells the row 4 guy that he's row 3. And then row 4 guy's like, all right, like I'm row 4 because the guy in front of me told me he's row 3. And then the row 4 guy tells me finally that he's row 4. So then I'm like, okay, I must be row 5. So it's the same way, like you're calling each function and that's just adding to the call stack. And then you're not going to get answers until the last guy gives you his answer. And then now everybody else can get their answer based on this last guy's answer. And then, factorial 4 is 4 times factorial 3, but factorial 3 has a return value now. Factorial 3 is 6. And then now factorial 5 is 5 times factorial 4, but factorial 4 is done running and its return value is 24. So now we're able to get the final return value of factorial 5. It's 120. And that is pretty much it for factorials. Are there any questions about this? Okay, so just some big examples are key takeaways are write your base case first. So always test the simplest inputs and outputs. So if we want to, going back to the sum everything in an array example, if we wanted to figure out the sum of everything in an array, maybe we should figure out what's the sum of an empty array. If people wanted us to reverse a string, what's an empty string reversed? Like the most simplest, almost disregardable case we should think about in this case, because that's going to usually be your base case. And then write your base case, test it using the simplest possible input. So it's good to just work from the bottom up. So, first test in this, if we were trying to sum a list, right? First test on a list that's empty. And then this, we could just say defaults to 0 as the sum. And then test on a list that's 1. And this could just be that element, right? And then test on it, and then gradually get bigger in order to figure out how to solve the problem. So it's just basically saying start small and work your way up. So we can use recursion with any data type in JavaScript. I kind of went over this example already, but basically, if we're asked to recurse through an array or a string, the base case is when the string is empty or it has a length of 1. So finding sum of numbers in an array, basically if the length is 1, then it's just that number. That's the base case. I'll go over the sum of array 1, and then I'll also do reversing a string recursively as well. I'll do some more examples so that you guys can see. But basically, we always want to start with a base case. We always want to remember there has to be a case where the function does not call itself. And then always start small. Always start with the simplest cases. So if there's, if we're summing an array, try doing sum of an array of empty array, and then try an array with just one thing inside, and then try 2 things, and then try 3 things. It's factorials. Start with factorial 0, then do factorial 1, then 2, then 3. Like try doing it smaller first, and then work your way up. And yeah, if you get stuck, just try solving it with a loop, and see if you could maybe break that loop down into, break that large problem down into smaller subproblems. That's pretty much it for the lecture part. So let's go with how to actually do this recursively. So here I'd say, if my base case might be if the list.length equals 0, right? So if there's just an empty array, then I'll just return 0. And that's my base case. And let's just see if it works. When I do sum of empty list, it should give me 0. Cool. And that's like half the battle right there, is like basically we're done almost. But now we need the case where it's the recursive case. And so here we could do something like, okay, so if my thing is 1, I need to somehow get that value, right? So I need to say, return list at 0, because I need to access this value. And then I could say plus, and then I need to recurse. So I need to do sum of, and then I need to make this input smaller and smaller. So I need to cut the length somehow. So I need to get the length closer to 0. So if the length is 1 right now, I need to somehow cut the length to be 0. So I'll just do list.slice of 1. And that should give me I think that gives me an empty array. Let me see. Array is 1. And then I do array.slice 1. Yeah, it just gives me an empty array. So in this particular case, I would return 1 plus sum of the list sliced off. So like everything to the right of 1, which is just an empty array in this case because there's nothing else after it. And then that just returns 0. So sum of an empty array is interchangeable with 0. And then I'm just doing that first element plus an empty array, and that will equal to 1. So if I do, let's get one more complicated than that, so 2. So this is false, right? The list length is 2. So we just return 1, which is the first element, plus sum of 2. And then sum of 2, because we sliced the first index off, so we have just an array of 2 now. And then this is basically going to equal to 2 because it'll go here and then it'll say return 2 plus sum of empty array, and that's just 0. So that'll eventually return 2, and then now we'll just get 3 because sum of 2 equals to 2, and then it just returns 1 plus 2, which just should equal 3. So yeah, before we were doing in factorial, we were doing n minus 1 because it was an integer. But because this input is an array, we can't really just subtract 1. But what we can do with arrays is we can slice. So we can slice off bits and pieces. So, if it's 1, 2, 3, 4, 5, 6, we can just do 1 plus the rest of the array sliced off. So we're breaking it down at each step. We're breaking it down one by one by one at each iteration. And yeah. Are there any questions on this particular implementation? So let's just try reversing a string. So we have string, and then we'll say, oh look, if the string dot length equals 0, if it's an empty string, then I'm just going to return the string. That's my base case. So when I want to reverse string of empty string, let's just say it should just be an empty string. Else, now we have the recursive case. Now we want to reverse the string, so we could say something like string. We could do something like return string at string.length minus 1. So that last character plus reverse string.slice 1. Wait, let me think. No. String dot. Because essentially, if I have like A, B, C, I'm doing the reverse version is C plus reverse AB. So I actually need to cut the last string.slice 0 to string.length minus 2. Basically, I need to cut the last one off each time, so it gets closer and closer. And then that will equal CB plus reverse A. And then that will equal CBA plus reverse an empty string. And then empty string is just that string. So, or hold on. Yeah, empty string will just return an empty string, and then it would just be plus an empty string, and CBA will be returned eventually, I believe. So let me try this. I think I'm missing that. Yeah. So basically this string.slice 0, 1, it basically cuts the last element off at each iteration. But basically the main ideas here are that, if you're working with an integer, you probably want to decrement it so it gets close to the base case. If you're working with strings and lists, you probably want to do something like slice to get this input to be smaller and smaller each time so that it eventually hits this base case. So Arthur asks, couldn't we pop? Yes, we could. Yes, I believe we could. So we could just do list dot slice 1. Or it wouldn't be pop because in this case we're doing 1, 2, 3. So we're slicing. So it would be like unshift or shift or whatever, because we would first be calling this, and then that would be 1 plus 1, 2, like function of 1, 2. So wait, hold on. 2, 3. Sorry. And so we need to do whatever gets rid of the first element, which I think is unshift or adds. So I think it's shift. I'm not 100% sure this will work because it might, because it's mutating the array, because these mutate the array, it could mess with things, but we can try it. Oh wait, shift will actually return, I think it returns that element. So yeah, that would be tricky because now it's just going to return 1. So it's just going to be sum of, so we could just do like list dot. Yeah, it'd just be more tricky. Like I'd have to do like let first element equals list 0, and then I could do maybe like list dot shift, and then pass the list in, that new list in, and then first element, and try it. Yeah, it still works. But it's just confusing now because it looks a little more confusing to me because it looks like you're passing the same list each time. So it doesn't look like I'm making progress towards this. So when I just use slice 1, it makes it look like, yeah, I'm like cutting it at each step. So I'm getting closer and closer to the, getting closer and closer to the base case. But you could use slice too, or shift. But yeah, the main ideas are when you're working with arrays and recursion, each recursive step, you kind of want to slim down that array, trim it down, either from the beginning or the end, like break it down by 1 element. And then for strings, you do want to do the same thing where you're trimming, here I'm trimming the end, but you could trim the start if you want. Like here, I'm trimming the start. Here, I'm trimming the end. But each time you need to trim, each recursive case, you need to trim it down so that it eventually hits the base case. Because otherwise, it's just going to eat up all the memory in your call stack, and you're never going to return anything. And it's just going to blow up your program. So yeah, I really like recursion. I think it's interesting. It's challenging for sure, but if you guys practice this enough, then it's a cool, different way to like approach problems. It's just breaking it down into the smallest possible case and then working your way up from there. But it's definitely challenging. So definitely need to practice this and just understand that, you know, these returns, it's tricky with these returns because like not having this return just means that this will be undefined because why this is undefined is because when you call sum of 1, 2, 3, it won't go into this return. It'll go into this else. And then you will recursively call the function. Don't get me wrong. Like you're still going to call the function recursively and everything's going to happen as you would expect it to. But we're never going to be able to extract the value of this because we're just running code. We're not returning it from the function. So we're not able to capture it in a variable and do anything meaningful with it. So a lot of times people will forget the return, but you need it if you want to do anything with the actual function invocation and saving it to a variable and such. So yeah, that concludes the lecture. Feel free to take a breather. I'll assign the breakout rooms for you guys now and unlock the workshop, and you guys can feel free to tackle these problems. Do we have a fellow on with us today by any chance? Any fellows? If not, feel free to call me into one of the breakout rooms, but I will be away for about 10 minutes and then I'll be back. So there might be a little bit of gap time, but yeah, feel free to bring me into any rooms if you guys have trouble with anything. Stop the share.